Okay. Thank you everyone for being here today. We're excited to continue our conversation with researchers at the Robotics Institute. The Summer Scholars Program is an opportunity for students from around the world to come and do research with really leaders in the field. And there's such a breadth of research being done at the Robotics Institute that this summer we have 58 scholars. We're entirely remote. So they're coming from over 14 different countries, and RISS has hosted students from over 50 countries, and it was founded in 2006. The Robotics Institute is one of the world's largest university-affiliated research groups. So if there's something being done in robotics, it's probably being done here, and there's some amazing research. So today we're going to hear from Dr. Maxim Likhachev. Max leads the SearchBased Planning Lab at the Institute, and he's going to share his work there, and he's going to share his passion for the research. We're going to get to talk to him a little bit about his career path and working with from basic research to commercialization and his experiences in between. So I'd like to welcome all of you that are joining us here in the Zoom room and on YouTube as well. We've got a really good group. Just a few things about housekeeping. We have a link that was shared with you. I'm going to drop it into the Zoom, and if you're on YouTube, you have that link where we're going to be handling all of the questions there. So you'll have a chance to ask questions, to upvote, and at the end of the session, we'll have a really good conversation with Max. So think about what you'd like to explore a little bit further, and we'll be happy to have that conversation at the end. So Max, welcome, and thank you so much for joining us today.
Yeah, thank you very much, Rachel. So let me share the screen. All right. Let's see. Can you guys see my screen all right?
Absolutely, perfect.
Okay, perfect. All right, so thanks again, Rachel. I'm also very much happy to see everybody here. I wish we were meeting in person, but you know, that's the best we can do, and I'm just glad to see a good crowd of folks. What I'll talk about is the research that my group does on search-based planning for robotic systems. I'm kind of happy to answer any questions you may have all throughout the talk, as long as you somehow let me know that there is a question, either by shouting it out or by sending it in the chat, and then maybe Rachel or somebody will let me know that there is a question. All right, so I'm a professor affiliated with the Robotics Institute, also affiliated with NREC. A few slides on kind of a just general focus of my group. I'm very much interested in the specific area in robotics, which is about planning and decision making. So how does a robot decide what to do next, and how to do that? Sorry. And kind of in all that stuff within that area, I'm very much interested in developing general algorithmic methods that apply to wide spectrum of systems, and some of those systems at the bottom are the system that my lab has worked on, but this is kind of just a sample of those robotic systems. So kind of we're thinking of developing those general algorithms, and then thinking about how to utilize them to control arms, ground vehicles, aerial vehicles, and so on. And another kind of aspect that's important to me is to make sure that those algorithms are rigorous and have rigorous theoretical guarantees, because I strongly believe that it's important to be able to analyze the algorithms that we develop, and that helps us analyze the behavior of the entire robotic systems, which is very important. So in particular, kind of approach that we take to planning is what's called the search-based planning. And in a kind of in a nutshell, at a very high level, that corresponds to the approach which takes the planning problem, whatever that might be, whether it's a motion planning problem, a task planning problem, whatever, and constructing a systematic graph representation of it, and then searching that graph for a solution using a graph search technique. So, some of this most kind of rudimentary problems in planning problems in robotics is planning for a 2D robot. So imagine you have a 2D robot and it needs to navigate from one point to the other, where you have obstacles potentially on the way. So you can take this entire environment and discretize it. So you put a grid on top of it. So those small cells, all of the same size, and then you convert that grid into a graph where every single cell that you have in this grid corresponds to a state. And then you have edges connecting those vertices in this graph to the adjacent cells, as long as those adjacent cells are free of obstacles, right? So this is kind of the most basic version of graph construction. And then once you have that graph, you can search this graph for a solution from a vertex that corresponds to the start state where the robot is currently at, to a vertex that corresponds to the goal state where the robot needs to go. And then once you have a path through this graph, you can kind of translate it back to the physical world, and that gives you the path that the robot should follow. Now, this is as I said, this is kind of the simplest example of search-based planning. Of course, a lot of systems are much more complex than that. So, for example, if we're talking about planning for a vehicle, then you may have to construct a more complex graph, like a lattice-based graph, where you have motion primitives that capture what the vehicle can do. Those are kind of offline constructed, kinodynamically feasible short motion primitives, and then you can construct a graph by taking that set of motion primitives and translating and rotating it to every single state that may be encountered by the search. So you can construct a graph this way, and then you search that graph for a solution, and that solution would correspond to a kinodynamically feasible motion that the vehicle can follow. So basically, the bottom line is that when we're talking about a search-based planning, we should not be just thinking about a simple 2D grid. It can be in much high dimensions. It could also be kind of constructed in a much more sophisticated fashion than just discretizing the environment and connecting to the neighboring cells. So this is kind of at a high level what the search-based planning is. And those two steps, construction of a graph and then searching a graph, both of them are very, very important. And a lot of research is going on into both of those two steps. In addition, those two steps are often can be interleaved so that you don't construct the graph first in its full entirety and then search. That may not be feasible, and instead, usually for high dimensional planning problems, you actually interleave those two steps together so that you start the search, and then as the search progresses, only then you kind of construct the graph and the portion of the graph that the search needs to access, as opposed to the entire graph. So the kind of on the positive side, the search-based planning provides rigorous guarantees on solution quality, because you have a kind of a very good systematic approach to construction of a graph. You have a good systematic approach typically to searching this graph. So it provides a good cost minimization. So solution that you're getting typically have rigorous guarantees on how close to optimal it is. And it's also has a property of typically providing consistency in a solution, meaning that for similar planning problems, you're getting similar solutions. And that's important, and particularly in manufacturing domains, or when there is an interaction with people, where you want to be able to kind of predict the behavior of the robot. And in such scenarios, if the robot generates similar plans to similar problems, that often contributes to being able to predict how the robot will behave, to have a better coordination with the robot, and so on. So we focus on a lot of different applications. I'll mention few that are quite extensive applications for us. Number one is autonomous manipulation, in particular in manufacturing. So let's say you have a robot like this PR2 or some other robot that needs to operate in an environment and needs to, let's say, working at a conveyor, it needs to detect objects, grab them off a conveyor and put elsewhere. So here's a kind of a planning problem where we need to be able to plan for the arms to pick up those objects in real time, and it needs to be done fast and very consistently. Another example is kind of also from manufacturing is assembly. So here's a PR2 robot building a 3D structure. It actually is a birdhouse. And it needs to figure out the order in which it will put those pieces together. It needs to figure out how to move the arms. It also has control over the nail gun that it's holding. So it has both the planning at the task level, meaning figuring out the order in which the object needs to be assembled, as well as the motion planning, meaning that how do you move the arms, how do you grasp things, and so on. Here's another one, and that one is more on the commercialization side of our efforts on the, for manipulation. So this is a industrial cuckoo arm. This is done in collaboration with NRAC. Industrial cuckoo arm that does paint stripping of the aircraft, and it also has the mobile base. It's a kind of very large robot, and this is doing paint stripping of F-16. So once again, this is an example where you want to have solutions that are as optimal as possible. It's very important that systems like that don't do some kind of have spurious behavior or do some random motions. And it's also important that you have very consistent solutions, meaning the similar solutions to the same planning problems, because you want to have an operator who kind of has a full trust in the behavior of the robot. So my lab does a lot of kind of work on autonomous manipulation domains like this. We also do quite a bit of work on aerial vehicles. So here's a few examples. Here is the one on the left is the robot that we built, quadrotor. The one on the right is a K-MAX helicopter that was done in collaboration with Lockheed Martin. And then the one at the bottom is a project with Mitsubishi, where we have kind of several large aircraft outdoors doing autonomous surveillance. In all those cases, we're doing planning for those vehicles to have flight through partially known environments. So the one that on the right, K-MAX helicopter was flying at about 100 knots. Now the one on the left, the small quadrotor, is flying obviously much slower, but then on the other hand, it's going through rather cluttered spaces. So, and it builds the map, and as it builds the map, it has to plan and replan. So a lot of the algorithms that we develop, as I said before, they're kind of general enough that the same algorithm can be utilized for manipulation as well as aerial vehicles. And even though I'm not showing here, there's all kind of a number of other type of robotic systems that we worked on, including humanoids, quadrupeds, teams of robots, ground vehicles, and all those systems utilize kind of underlying the same algorithms. So what are the challenges, the research challenges that we're actually looking at? One of the main research challenge is to make sure that you have those planning algorithms that can generate solutions in real time. So if you think about it, let's say on an aerial vehicle or even a manipulation platform, you need to have a planner that constantly generates and regenerates solutions in response to the sensor data that is being received. So as the helicopter flies, it gathers information about the environment, it updates its map, it needs to replan. This robot here, PR2, carries that picture, it also utilizes onboard sensors to detect objects, people in the environment, to detect any sort of misplacement of obstacles and so on, and it needs to replan. Now, let's say on these aerial vehicles, replanning needs to be happening, let's say at 2 hertz, or every 500 milliseconds, it needs to generate a new plan. Maybe on the PR2, it needs to replan once in 2 or 3 seconds. Now, to make sure that those time constraints are met can be quite challenging. In particular, if you think about it, let's say for the aerial vehicle, the planning happens in 5 dimensions. So X, Y, Z obviously flies in the 3D. Orientation of the vehicle typically important, and the velocity at which it flies is important. So if you kind of discretize it, relatively large area like a 10 kilometer by 10 kilometer, you're getting a half a billion states in the graph. Now, of course, as I said before, you typically never approach the planning problem by constructing the entire graph and then searching over it. You interleave those two things together, so that you only need to construct the portion of the graph that will be searched. But nevertheless, even with that, it's a large number of states. So it's a very large graph. If you look at the planning for manipulation platform like this PR2, that robot for that particular planning problem is a 12-dimensional planning problem. And if you discretize it, then it becomes 10 to 19 states. So it's a very, very large graph. So the question is, how do you, how can you have planning algorithms that operate in large state spaces like this in real time? So those are kind of some of the challenges that we often have to look at in my lab. Now, for those folks who are familiar with planning, they kind of might be familiar. There are 2 predominant classes to planning. One is search-based planning approaches, in particular the one that rely on optimal graph search techniques like the A-star, D-star. And those techniques, as I said before, have those nice properties that they provide rigorous guarantees on the optimality of a solution, completeness, meaning that if there is a solution, they'll find it, given the discretization. They typically provide a very good cost minimization, and they have that consistency property. Now, on the other hand, once we kind of go to higher than 2D planning problems, then it really hurts us the fact that those algorithms are computationally pretty expensive, and they consume quite a bit of memory. The other class of the algorithms are sampling-based approaches, which typically rely on kind of taking the entire planning space and constructing a random graphs over it. So basically generating random samples over it and trying to connect those samples and searching over those type of graphs. And this operations, once again, can be interleaved, where you don't have to construct the graph beforehand, but interleaved with the search itself. But the difference is that they rely on the fact that a lot of those environments are kind of sparse, much more benign, and therefore you can kind of put a random graph over it. They're typically very fast in high dimensions and consume lower memory. Um, and for high D, path and motion planning quite often used. The downsides, on the other hand, of course, is that the completeness and optimality are in the limit of the number of samples that are being drawn to construct this graph. And because of that, typically when you're operating them at frequency of whatever, once, half a second or one episode per second, then the cost minimization, it's much harder to do very good cost minimization. Due to randomness, they also typically don't provide solution consistency, so that the ability to generate the same answers to similar planning queries, they cannot do that given the randomized nature of those algorithms. So a lot of the work that my lab does is on trying to take the kind of search-based planning approaches, the one on the left, and move it to a high-dimensional state space. So overcome their limitations with respect to the dimensionality of planning problems and be able to utilize them when we're talking about planning for aerial vehicles, for manipulation, and so on. The kind of few key ideas that are quite often being utilized in my lab in particular are the following. So number one is that if we are not going for the probably optimal solution, but we can actually go for the solutions of bounded suboptimality, then it gives us a way to construct much faster algorithms. And I'll show some kind of examples of that. So that's number one. So kind of going for this bounded optimality solutions as opposed to probably optimal solutions can give us a lot of speed up. And at the same time, we still have a very good cost minimization. We still have a consistency of solutions and so on. The other kind of key idea is that if we're thinking about a high dimensional planning problem, even planning for aerial vehicles or manipulation and so on, it's often is the case that you can take that complex high-dimensional planning problem and decompose it into one or more lower dimensional planning problems, solve those, and then solutions to those can be used to guide high-dimensional search quite effectively. And I'll show examples of that as well. So those are the two things, kind of two key ideas that I'll talk throughout this talk, and once again, happy to answer any questions that might come up. So my agenda for the remainder of the talk is as follows. So I'll give some background on heuristic search, since I assume that not everybody might be familiar on it. I will then talk about how we can guide the heuristic search with solutions to lower dimensional planning problems. I will also talk about how we can utilize multiple lower dimensional planning problems, solutions to multiple lower dimensional planning problems. And in particular, I'll talk about one of the algorithms that my group has introduced, multiheuristic A-star. And then I'll finish up with some of the kind of thoughts on research directions that my lab has pursued in the last few years. All right, so let's see. The going back to the search-based planning, as I said, there are those two steps: generation of the graph representation, and then searching the graph for a solution. I already kind of gave some high-level ideas about how graphs can be generated. Typically, it's a very important and an interesting topic. I will not kind of dive into any more details on that. Instead, I'll give an example of one of the main algorithms in search-based planning, in particular A-star search. I'll explain that. And then that will provide us the background necessary to understand the remainder of the talk. So imagine you have a graph shown at the bottom, and that graph has been constructed usually from whatever the technique that we used, whether it's a grid or whether it's a lattice base, doesn't matter. But we have a graph. We have start and the goal vertices. We have the edge costs in it, and we're looking for a least cost path in this graph. So many searches, including A-star, they work by computing optimal G-values. Those G-values correspond to the cost of least cost path from a start state to a corresponding state. So for example, the G-value of the goal state is 5. And there are two paths how you can get from the start to the goal, going over the top or going through the bottom. The one going over the top has the smaller cost, in particular, it has a least cost path. It's a least cost path of getting from the start to the goal, and its cost is 5, and that's why the G-value of that goal state is 5. So if you have optimal G-values, it can be shown that they satisfy this particular equation where the G-value of any state is exactly equal to the minimum of the G-value of the predecessors plus the cost of a transition. So for example, here, the G-value of that goal state is exactly equal to the minimum between 3 plus 2 versus 5 plus 1. So 3 plus 2 is 5, 5 plus 1 is 6. So the minimum between the two is 3 plus 2, which is 5, and that's why the G-value of the goal state is 5. So you have that local property where somebody tells you that for every state you have optimal G-values, then you know that it should be the case that the G-value of that state is exactly equal to the minimum of the G-value of predecessor plus the cost of a transition. It's good to know because if somebody gives you, if there is a search that computed those optimal G-values, then an optimal path from the start to the goal can be easily reconstructed by what's called the backtracking, where you start at the goal state and you always move to the state that minimizes that equation of the minimum of the G-value of predecessor plus the cost of a transition, and you can keep on going like that until you hit the start state. So this way you reconstruct that least cost path, and then you can give that least cost path to the robot for execution. So that's kind of why the G-values on its own are important to be able to compute. And as I said before, many searchers work by computing those optimal G-values. Now, A-star search does not compute optimal G-values for all the states in the graph. The graph could be huge. A-star search works by computing those optimal G-values for a subset of the states, subset of the vertices in the graph. In particular, that subset is a set of states that are relevant to your optimal path. To do so, to identify what are the relevant states, and kind of throughout the operation of the algorithm, it maintains two variables. So number one, it maintains that G-value of a state. And at any point of time, it's the cost of the best path found so far from the start to a state. So for any state S in the graph, A-star, the G-value that it maintains for that state is the cost of the best path it found so far to that state. The other variable it has is a heuristic function, which is an estimate of the remaining path from that state S to the goal. So for every state, it has that heuristic function. It also has to be an underestimate, meaning that it does not overestimate the actual cost of that remaining path. So in robotics, one super popular heuristic function is Euclidean distance. So if you think about a motion planning problem, like let's say planning for a 2D robot to get to its goal, then for any state, for any cell that you have, so let's say you're doing a 2D planning by discretizing the state space, like I've shown earlier, and constructing a graph, corresponding graph, then for every single vertex, for every single cell that you have, the heuristic function could be Euclidean distance, just the straight line distance from that cell to the goal. Now, of course, it's an underestimate because it doesn't account for obstacles, right? So it doesn't go around the obstacles. It's very, very fast to compute. And it's also an underestimate because it also does not account for the fact that this grid is being constructed where you're only allowed to move to its neighbors, whereas if you're looking at Euclidean distance, it's just a straight line segment. So it's a super fast, easy to compute heuristic function. But as I'll show later, it's very often for more complex planar problems, it's not a good heuristic function. So let's kind of go through the explanation of A-star search. So A-star search itself works as follows. It initializes the graph where the g-value of every single state is infinity because it hasn't found a path to any one of those states yet, except for the start state where the g-value is 0 because the path from the start state to itself is 0. And then it keeps on expanding states starting from the start state until it expands the goal state. And I'll explain in a second what it means. So at any point in time, it maintains an open list, which is a set of candidates for expansion, where initially the open list contains just the start state. That open list is typically a heap that is ordered by priority, and at any point of time, it always picks a state to expand next that has the smallest f value, which is the summation of the g value of a state plus the age. So for any state S, f value is effectively the estimate of a cost to go from the start state to the goal state via that state S, because the g value gives us the cost of going from the start state to that state S, plus the h value, which is an estimate of the remaining portion. So it picks that state with the smallest f value and expands it. It can be shown that for every single expanded state, it's guaranteed that the g value of that state is already provably optimal. So we have the cost of a least cost path to it. The expansion itself is means as follows. So it takes that state. First of all, it says, well, we're done computing that state. And then the other thing is that what it does, it propagates the path that it found to that state S to all of its successors. In particular, it looks at all the successors and sees if their g values can be improved using the path to that state S. So if their g value is larger than the g value of that state S that is expanding plus the cost of a transition from going from that state S to S prime, then it updates the g value of that successor S prime and puts it into the open list as a candidate for expansion. So in closed list, this contains all the states that have already been computed. So we know that we have optimal paths to them. So let's kind of go through an example of this on this simple graph. So we start out, as I said before, with the start state as the only state in the open list. We have selected that state for expansion, and we're looking at all of the successors. There is only one successor, namely state S2. Its g value is currently at infinity. So of course it's larger than the g value of the state that we're expanding, meaning start state, which is 0, plus the cost of a transition 1. So infinity is larger than 1. So we're updating the g value of that state S2 and putting it into the open list. So after the expansion of the start state, S2 is in the open list, start state is enclosed, it's done. And the next state for us to expand would be the state S2. As we expand state S2, there are two successors. Both of their g values will be updated using the path that we just found to that state S2. So for the S1, the g value will be 1 plus 2. And for S4, the g value will be 1 plus 1. So after the expansion of S2, we have both of their successors have their g values updated, and they're both being added to the open list. Now, at this point, once again, we have to select the next state to expand. The next state to expand will be the one that has the smallest F value. Well, out of those two, they both have the same F value as G plus H, so it doesn't really matter which one. So let's say we select the state S1 to expand. As we expand state S1, its successor, namely S goal, will have its G value updated. As it gets updated, so it gets up to 5, it also gets inserted into the open list. So theoretically, at this point, we have a path to the goal state. However, that path is not yet guaranteed to be provably optimal because the goal state hasn't been yet expanded. So the next state to expand is actually S4 because it has a smaller F value. And as we expand S4, its successor S3 will have its G value updated. So after that expansion, we'll have S3 in the open list. It will have an F value of 5 plus 1, which is 6. And of course, therefore, the next state to be expanded will be S goal. So we expand the S goal, and at this point, we're done. So as you see, the search has not actually expanded S3. And more generally, like if you had a huge graph, then there would be lots and lots of states that have not been expanded by a star search, yet it can guarantee that if we were to do that backtracking step that I said before, like start at the goal state and go to the state that minimizes the G value plus the cost of transition, we would have reconstructed a least cost path. So this is indeed the case here, where we do the backtracking and we have the least cost path computed, and that can be given to for execution. So once again, it has those nice properties where for every expanded state, the G value is optimal. For every other state, it's an upper bound, and we can construct a least cost path by doing that backtracking. So A-star search kind of has in general, is a very, very nice algorithm. It guaranteed to return a least cost path, as I just shown. It also has a nice property that it performs a provably minimal amount of work that one can do in order to construct a provably optimal solution, as long as you measure the amount of work in terms of the state expanded. So it's kind of optimal in terms of the amount of computation it can do. The problem is that for planning problems, for complex planning problems in particular, as you go beyond 2D, the amount of work it has to do it can really be huge still. So let's, in particular, the heuristic function makes a huge difference. So let's look at the kind of graphical example of that. So imagine if I were to do a search from the start to the goal without any heuristic function. So in other words, the way to think about it is a heuristic function, which is equal to 0. Then the amount of work, so the states that get expanded would be something along that line, where it will just kind of expanding states in all the directions and until that circle encompasses the goal state. By the way, that red thing is meant to be an obstacle. Now, if I were to do the same search with a heuristic function that, let's say, Euclidean distance, that dramatically reduces the amount of effort the search has to do. So you would have a kind of like an ellipse, and it still computes a provably optimal solution. So you can immediately see that heuristic function can have an enormous effect on the amount of computation the search does. However, if you think about it kind of larger planning problems, not just 2D, but going to 4, 5D, this ellipse, having all the states computed within this ellipse, could still be a lot of states. So, you know, trying to compute all those states and satisfy, let's say, 500 millisecond planning cycle can be hard. So the weighted A-star search is a very, very simple modification of A-star search, where you take the heuristics that you're given to you and you just inflate them by constant larger than 1. It allows you to trade off optimality of the solution for speed. So let's just see what happens here. So we take the Euclidean distance heuristic function and we inflate it by W. In particular, we inflate a very large W. Then the amount of work that the search will do will kind of graphically will be something along that line, where it shoots straight for the goal. It tries to get us to the goal as quickly as possible. Then it hits the local minimum. In order for it to understand how to escape this local minimum, it has to fill it up. So it has to kind of expand all the states within this local minimum, identify how it can proceed. As soon as it identifies how it can proceed, it can once again shoot straight to the goal. So it's a tremendously less computational effort than a star can be. The other good thing about it is that even though it's no longer optimal solution, you could see it's suboptimal as compared to the optimal that we saw previously. It can also be shown that the solution is W suboptimal, meaning that its cost is no more than W times the cost of an optimal solution, even though we don't have an optimal solution. It's a nice algorithm, very, very simple modification to a star search, and typically can give us a much better speed performance than a star search. Now, clearly, it still needs to fill in this local minimum to find the way out of it. And that could be quite costly in a high-dimensional state spaces. So a lot of research needs to go into figuring out a heuristic function that results in a shallow, small local minima as opposed to large. And this is where this idea that I mentioned earlier, where very often you can take a complex planning problem and you can construct a lower dimensional version of it, and you can compute a heuristic function on that lower dimensional version, and that will give you quite a substantial speed up to the entire planning framework. So let me give kind of a few examples of that. Here is a planning for ground vehicle SUV, and this is planning an XY orientation and velocity of the vehicle. If you were just to do Euclidean distance, then this obstacle, that red obstacle that is kind of on the way between the start and the goal, would give it a huge local minimum to the search. Because it says, well, you can just proceed forward, and then the search will expand all the states here. If you were to take the heuristic function and compute it on 2D, where you put a grid over this just 2D space, and you run, Dijkstra search or something like that, so to compute the distances in 2D with respect to the goal, accounting for the obstacles, then that gives you an underestimate on the cost to goal, because it doesn't consider the dynamics constraint of the vehicle. And at the same time, it gives you a much better guidance to the search than Euclidean distance. So you spend time on doing this 2D planning, but then that time, let's say 10 milliseconds that goes into that, can give you a huge speed up in terms of this original 4-dimensional planning problem. It can literally result in going from, let's say, 10 seconds of planning to 100 milliseconds of planning. So here is the example of this running on the this SUV, where it's planning in this 4-dimensional state space, XY orientation and velocity, that's that red path, and it's planning on a 100 millisecond planning cycle, and it runs every 100 milliseconds. It executes this 2-dimensional search to compute a heuristic. It goes, typically it takes like 40 milliseconds or something like that. And then the result of that is fed into the 4-dimensional planner as a heuristic function. So that allows us to kind of maintain this 100 millisecond performance guarantee. So similarly, the let me. Yeah, so anyway, we'll keep on going. So let me kind of go to the next example. So similarly, in when we're planning for the aerial vehicle, that's kind of that's the example that I've shown earlier, both indoors and outdoors. the planner itself needs to generate a solution roughly at about, I think it's 500 milliseconds. The heuristic here can be a 3D heuristic. So you're running a 3D Dijkstra in this 3D over the 3D grid. That may take, let's say, 200 milliseconds, but that gives you a much better heuristic function than Euclidean distance, and you can feed that into this 5-dimensional planner, and with everything, that 5-dimensional planner then is able to maintain the 500 millisecond cycle rate. And then that example that I've shown earlier with the manipulation, that is a 7-dimensional planning problem. So the arm itself is a 7-dimensional arm. And the heuristic function is a 3D distance for the end effect. So once again, it's a 3-dimensional search that computes the distance for the end effector to get to the goal while accounting for obstacles. That takes, computational heuristic itself takes about 100 milliseconds or so, but then that allows the planner, full 7-dimensional planner, to compute a solution within a matter of another few hundred milliseconds. So this is kind of a general idea that you can use a solution to low-dimensional planning problems to guide the full-dimensional search. Now, in a complex robotic systems like PR2, when you're doing the full-body planning, there you could potentially have multiple ways how you can construct a low-dimensional space. So let's say, if you think about it, this PR2, all right, it moves the body. The body itself is, you can think of it as a 3-degree of freedom, X, Y, and orientation. And then it's also moving the arms, in particular, it's holding this object. So you can plan for the 6-dimensional trajectory of the object itself. So there's at least those 2 ways how you can compute it. So if you take just one of those low-dimensional solutions, so let's say you construct a heuristic function by just doing a 2D planning for the base of the robot, and using that heuristic function to guide the full 12-dimensional search, then the search still getting stuck. So here's it shows the states that are getting expanded by the search, this 12-dimensional search, and as you can see, it's getting stuck. And the reason it's getting stuck, the heuristic, the 2D heuristic, says that, yeah, you got to move the base towards the goal. The goal is, by the way, here where it needs to place the object. And this is the heat map showing the how the heuristic function, the 2D heuristic function, is getting closer to the goal. It gets blue, more and more blue. Now it's getting stuck because it needs to figure out how to reorient the picture. And reorienting the picture has nothing to do with the moving the base. It's more the coordination of the arms. And that, of course, is a high-dimensional planning problem on its own. So there is nothing in the heuristic function that guides this reorientation of the picture. And that creates a large local minimum for the search. And of course, eventually it will find solution, but it takes forever. Now, one can construct more sophisticated heuristic functions. For example, one can say, why don't I have a heuristic function that computes the summation of the base distance, so that 2D distance, plus the difference between the orientation of the object itself with the goal orientation. So the goal orientation, it needs to be the end flat on the table. So that is certainly kind of a valid heuristic function. However, that heuristic function gets stuck right from the very beginning because it says, well, I mean, you've got to try to maintain as much as possible flat, whereas it needs to reorient to move forward. Another heuristic function, which actually is totally inadmissible, is a summation of the base distance plus the difference between the orientation of the object, like that picture, and the vertical orientation. Why is it useful potentially, heuristic function? Because in order to move through the narrow passageways, you actually do want to keep this object vertical, right? So if we take that heuristic function, that shows the states expanded, and we can see that the search progresses actually very well all the way towards the goal. But at the goal, it still cannot land this picture flat, because at the goal, it needs to be horizontal, whereas our heuristic says that it's a distance between the orientation of the object and vertical. So it kind of tries to guide the search towards the vertical. So both of those heuristic functions are kind of useful in different places, but neither one of them gets us where we need to be. So which kind of gives us a motivation to look at the planning problem where we can generate n arbitrary heuristic functions, not just one, but n. They all have different estimates, different ways to estimate the cost of the goal. And the question is, how can we utilize those n heuristic functions, or more generally, a bunch of inadmissible heuristic functions simultaneously? And particularly to do it in a way that provides those guarantees that we want. So with that, I'll give you a simple extension of A star search, what we call multi-heuristic A star, that allows us to do that effectively. So let's imagine we do have n inadmissible heuristics. What we can do, like the first variant, trivial variant, is we can run n independent weighted A star searches. So you run all of them simultaneously. Now, I mean, if we assume it's a sequential computing architecture, then we're talking about doing it in round robin, where we expand from a state from the Q1. Then after we're done with that, expand the state from a Q2, and then from Q3, and so on. So each search gets to expand one state, and then we come back to the search number one, and so on and so on. So if we do that, then and we can just hope that one of them reaches the goal. That certainly is a possibility. Now, the problem with that is that you could have a scenario that each one of those searches has its own local minimum, and it's just going to get stuck there. In particular, in the example that I've shown previously, that's what happens. You had like several heuristic functions, neither one of them got to the goal. On top of it, you're doing, if we have n searches, we're doing n times more work. And then finally, there is no completeness guarantees on this overall approach. So the kind of a simple extension of this simple idea that extends this framework is let the searchers collaborate with each other, meaning that as we find a path to a particular state and we expand that state in the search one, why don't we share the successes with all the other searches? So this way we're propagating the path found in the search one with the this information with the search 2 and search 3 and so on. So we literally, whenever we expand the state, we take the successes and we put the successes into the open list of all the other searches as well. Furthermore, we share the closed list. So we do not let state to be expanded more than once. So if a search 1 expanded a state S, then all the other searches don't need to do that expansion anymore, because we already have found the path to it and we already shared those successes with all the other searches. There is no point in re-expanding that state again. So that immediately gives us this kind of nice synergy between the searches, so that they can, one search can walk through whatever, and whenever it gets stuck on a particular local minimum, then the other search can circumvent that local minimum, and so on. So they share the efforts between each other, they share the paths they find between each other. Furthermore, because we're restricting and not allowing state to be expanded more than once across all the searches, even though we have n inadmissible heuristics, the amount of expansions we do is only 1 per state. So we kind of don't have that explosion of the computational efforts. The only other problem we have is that there's still no completeness guarantees, because those heuristics could be completely inadmissible. So that last problem can be fixed by adding what we call an anchor search. So an anchor search, if let's say we do have access to admissible heuristic, we can use the anchor search, which runs in addition to all the other searches. And in particular, it controls when those other searches can expand their state. And it can be shown that with this, the algorithm is complete, meaning that it will return solution if one exists and provides rigorous bounds on the suboptimality of a solution. So the way the anchor search is being used is a simple rule which says that whenever we're looking at any sort of a search I that we're thinking of expanding a state from it, if the priority, the minimum priority in the ith open list is less than or equal than W2, which is a user parameter, times the minimum priority in the anchor search, then we're allowing to do that expansion. And if this rule is not satisfied, then we have to expand states out of the anchor search. And as we do, the minimum priority within that anchor search will go up. And therefore, at some point, it's guaranteed that this inequality will be true. So with that simple rule, it can be shown, I'm not going to go through the details, but it can be shown that the algorithm is complete. The cost of the solution it finds is no more than W2 times the W, which is the inflation that we use to inflate the heuristics, times the cost of an optimal solution. So it's bounded suboptimal. And it can also be shown that each state is expanded at most twice, once within the anchor search and once across all the other inadmissible searches. So here's an example of the same this planning problem of moving the picture. So here's
Max, I'm going to interrupt just for a moment. We just have a few minutes to wrap up, and there are probably about 10 questions that came in. So I'll help facilitate questions in just a few minutes.
Okay, sure. So this actually, I think, is pretty much the last slide or something. It's close to the last slide on in terms of the actual technical topic. So let me show that the solution that was found here. So this shows the solution that was found, and the different colors correspond to different portions of the path found by different searchers. So the first one was blue, then green, and then yellow. Those correspond to different heuristics being utilized automatically. And this, of course, is the movie of this thing running on PR2 itself. So that's a multi-heuristic star search. Yeah, I'm going to skip it. Trust me, it puts this thing on the table. So the key points, I just want to make sure that the folks kind of get out of it is number one is if you're doing a search-based planning in terms of heuristics, there is much better heuristic function than just using Euclidean distance. In particular, you should think about it, lower dimensional planning problems that you can solve. And then the second thing is that if you do have multiple lower dimensional planning problems that you can construct, then you can just solve each one of them separately. Then you can use like something like multi-heuristic star search to utilize them quite effectively. I will probably stop here. I mean, in terms of research directions, I mean, I'm very much interested in integration of planning and learning. I mean, this is kind of a separate topic to discuss. I'm also very interested in use of simulation-based models in planning to generate plans that involve interaction with the environment. I will stop here, and you know, that's a photo of my lab, and see if we can kind of go through some of the questions.
Wonderful, Max. All the robots and the hardware look amazing there. There's a lot there. So the link to upvote questions is in the chat and on YouTube, so that's been shared out. I'm going to get us started with our first question, and then I'm going to introduce my colleague Rutav Shah to continue. So Max, one of the questions that came in is, how do you take into account external factors acting on the robot, such as a strong wind in the case of a drone? So broadly, when you're looking at the external factors, how do you take that into account?
Right. So I mean, multiple things, right? Typically there are kind of two parts to it. Number one is it's very, very important to have replanning. So the whole planning is a closed loop, meaning that as you see any sort of disturbances coming in, you react and replan. Now, if you have disturbances that are known to you a priori, so let's say you measure the wind ahead of time, so you have some sort of measuring system, then you can model that in. So your motion primitive that you use, I effectively, when you forward simulate them, you take those disturbances into account and you forward simulate the expected outcomes of this. That modifies your effectively model that you use for planning, and then you can plan under that. Now, of course, having said, given even with both of those kind of things that you should do, you should also rely quite a bit on the controller, underlying controller that follows the path and is kind of quite capable of closing the loop, even despite the fact that this path gets replanned. So it's kind of important that the entire system has this controller that's robust to some disturbances as well.
Okay, Rutav, I'm going to hand it over
Yeah.
to you.
Thank you so much for this wonderful talk. I'll just read. There are many questions in the here.
Sure.
Uh, Next question is, what are some of the planning challenges introduced when scaling from a drone to a larger aerial vehicle? Uh, yeah.
Yeah. Well, so yeah, it's an interesting one. So the drone, like we had a flying indoors. It's a smaller speeds. So it's like slow speeds, which is good. On the other hand, the typically we were interested to go through a very cluttered spaces, and because of this, the discretization of the entire space needs to be quite fine. So typically, it's something like no more than 5 centimeters a cell. So you're still getting a very, very large grid if we're talking about large areas. When you go to the outdoor systems like that KMAX helicopter, the speeds are much higher. So you have a very, very kind of fast flying. And therefore dynamics, it becomes important. So you have a velocity, you have to maintain the limits on kind of deceleration, acceleration, and the limits on how fast you can change your height and so on. But then on the other hand, the space itself is much simpler. So you have typically you'll have like a large no-fly zone here and there. So you no longer have those kind of a complex labyrinths and so on. So it's kind of pluses and minuses. The disturbances are definitely there on the outdoor systems. And then the other one is the areas over which it's flying. Those outdoor systems typically are very, very large. So it can be 10 by 10 kilometers or 30 by 30 kilometers. And then once you looking into this, then you typically would have to think about, well, can you do some sort of adaptive reasoning where larger, kind of farther away from the vehicle, you can think about it, discretization that is very coarse, whereas close to the vehicle, it's a much finer discretization. So you have to think about adaptive discretization, given that the areas are so large. Hopefully that kind of answers that question.
Okay. Yeah, thank you. Um, Moving on to the next question, is it really possible or feasible rather to inculcate time variable along with the other state variables to incorporate like dynamic obstacles while planning? Um,
Yeah, very much so. Yeah, I mean, you have to. So you're bringing in time as a dimension into the state space, and um, you typically have, like, if you're looking at the time, then you would also have velocity if you're in control of velocity. So in many cases, we are doing planning with time. Timing is an interesting dimension in a sense that it's only go up, it never goes down. And there are certain characteristics of that can be taken into account. So some of the works like safe interval path planning that I haven't explained here actually allows us to compress time into a state space where it's not just a dimension that grows unbounded, but it's rather for every single configuration of the robot, you're really only caring about the whether it's before or after dynamic obstacle crosses that particular place, that configuration. So you can kind of do compression on the state space to give you a much more compact planning representation. But let's say let's say you're looking at planning for self-driving vehicles on the highways. You absolutely have to plan with time as a dimension. There is no other way.
Mhm. Next question is, how do you search in a partially observable environment?
So it depends on what specifically domain we're talking about. Let's say navigation, let's say aerial vehicles. The number one approach, kind of the number one aspect of it is you always have to think about planning as a planning in a closed loop, meaning that you have to keep on replanning based on whatever the sensory updates you're getting. So the most common approach to dealing with a partially observable, partially known environments is you assume whatever you don't know is traversable, and then you plan through it, and as you get new information, you update the map and you replan, which means that you have to have a replanning fast and so on. Now, of course, there are some algorithms exist, including from our work, that allow you to plan under uncertainty. So proactively kind of reason about, well, even if this thing is abstracted, then I would have to take such and such G2 and generate the entire policy this way. It's computationally very expensive, substantially more expensive. And therefore, you kind of have to be careful when you should do it. There are certain cases where it really makes sense to do that. But in most of the scenarios, you shouldn't really do that because it's computationally very expensive and it doesn't give you as much value as you might think, because it relies on some model of you knowing the probability of this event happening and so on. And where does in reality, where does it come from anyway? So it's kind of my philosophical view on this thing is bring that planning under uncertainty when it's critical, but be 100% sure that you need it before you bring that in.
Yeah, there's one question here, a little bit out of the context, but for the opportunity for grad research in your laboratory, what are the technical skills you value the most? Um, Example, programming skills, electronics implementation, or any particular software?
Yeah. So, well, one of the kind of most important skill that I personally value the most is being super enthusiastic, super excited about robotics, and being willing to put in long hours in getting those all those robots move and fly and so on and so on. I think that's the most important thing, and being able to not get discouraged by all the different crashes that happen and so on. I have a number of my favorite movies are the ones where the robot crash into the walls and things like that. I think those are much more interesting to watch than the movies where everything works out fine. So apart from that, I typically, of course, do care a lot about folks having a strong programming background, because a lot of building those planners it requires having a high proficiency in programming and understanding how to implement efficient planners. So knowing C++ is important, to being comfortable with data structures. Knowing ROS is typically very important. Yeah, and then good analytical skills, being able to prove things and enjoy doing that is equally important, because as I said before, I mean, I personally like to have not just a system developed, but the algorithms developed that have rigorous theoretical properties.
That's wonderful. Thank you so much, Max, for your
Mhm.
sharing your lab and your work. I know that there were many questions that we were unable to get to, but in interest of everyone's time, I want to be respectful of that and just thank everyone for joining us today.